Many of you may never have heard of the Viking mission to Mars, especially you in the younger generation. But in 1976, NASA landed two of the most complex spacecraft ever launched on the surface of Mars. I happen to have had an experiment aboard one of those. The whole mission was dedicated towards the search for life on Mars, and my experiment was one of those that was a life detector. It was called the labeled release experiment, and I believe it did indeed find life on Mars. However, I'm going to tell you the tale of how this was not widely accepted, the 34-year fight I've had to have it accepted, where the situation stands now, and what I think we ought to do. My trip along the yellow brick road that went 440 million miles to Mars started on the yellow sands of Santa Monica Beach in California. There, as a public health engineer for the state of California, I was taking samples of seawater to have them analyzed for bacteria to see whether people could swim safely in the seawater. Much of the sewage from Los Angeles was being dumped at that time right into Santa Monica Bay, right where people were swimming. What bothered me about this was that after I took the sample, took it back to the laboratory, it took 3 or 4 days for the analyses and sometimes as long as a week for the reports to come back to me telling me what the status of the water was. On the basis of that, I was to quarantine or not quarantine stretches of the beach. Obviously, anyone could see that by the time the results came back, thousands of people had gone bathing in the water, and the results were of historic interest only. This did frustrate me. I went back to the District of Columbia, changing my jobs, where I worked for the DC Department of Public Health. And again, I was responsible for microbiological quality of water. This time, much more serious than just bathing water, but drinking water for the entire municipality. Every day, I sent sanitarians out to sample taps from distant parts of the city, bring them back to the laboratory for analysis, but alas, again, it was up to a week before we got results, and 1 million or so people had consumed the water by then. One day, the thought occurred to me that perhaps a simple modification of the standard method for analyzing water for microorganisms could speed the whole process up. The standard method consists of taking a sample suspected of containing microorganisms and placing a part of it into test tubes containing nutrient broths to grow the microorganisms. If indeed they grew, they would produce eventually bubbles, which could be seen. These took 1, 2, 3, 4 days before you could tell that there was something growing in the broth. What occurred to me was the use of radioisotopic carbon instead of plain old nutrients. I had some radioisotopic carbon nutrient made, and I tested this in the standard method, and I found that I could detect the microorganisms in a very short period of time. Well, in order to do this, however, I had first to make a proposal to the U.S. Atomic Energy Commission, win a small grant from them, then convince my boss, the head of the Department of Public Health, to take me to Georgetown University Med School, where the Department of Biochemistry welcomed the opportunity to have me devote 1 day a week in their laboratory to developing this method. As I just indicated, the method developed very quickly and successfully, so that within a couple of months, it was obvious that a new method was available that could detect as few as 10 microorganisms and could make the detection in record time of half hour, 1 hour, couple of hours at the most. So here was a way that we could tell in real time whether water was contaminated or not, be it bathing water, drinking water, swimming water, whatever. As a result, I wrote and published a couple of papers outlining this procedure, hoping that public health departments across the nation would adopt it. Alas, they did not. Why? Because in those days, radioisotopes was a bad word. People were scared of anything that was radioactive. Even though by the U.S. Atomic Energy Commission standards, I could drink tap water with as much of the radioisotope in it as was required for the test. So it was really a very tiny amount. Nonetheless, the word was enough to warn people away. So again, I was quite frustrated in that the states, barring one or two, did not adapt the method to their procedures. Well, one Christmas Eve, I found myself at a party where I was fortunate enough to bump into Dr. Keith Glennon, the first administrator of the newly formed National Aeronautics and Space Administration, NASA. During the course of the evening, I had a conversation with him, and I asked him whether NASA ever intended to look for life on Mars. He said, "Oh, yes, we do." He said, "As a matter of fact, I just hired a man to head up a biology department to do that." I said, "Oh, isn't that interesting? I have a method that I think might work on Mars." He said, "Well, if you do, why don't you go down and speak to this man, Dr. Clark Rand?" I said, "Gee, I'd love to do that." And he gave me Dr. Rand's number. I called him up the next workday. He invited me down. I described the method to him. He said, "Hey, that sounds great. We are just funding methods to look for life on other planets. We have only one other method so far funded. So write a proposal." I did write a proposal, and then I learned something about the government. It takes time. After my proposal was submitted, I waited a year before I found out one day by a letter that it was accepted. So here I was now funded in a little company that I had started to undertake a research program to develop the technique from that for drinking water to one to look for life on Mars. It was very exciting. I worked for 10 years in this development, and the first thing that I did was decide, since I don't know what the spacecraft is going to be like or what kind of support I would have, I'd better develop a technology that is pretty self-supporting, doesn't need any help. And I did develop this little machine, which you can see in the slide, that I called Gulliver, because it was going to distant places looking for Lilliputian tiny beings. And I thought this was a rather good name for it. The way it worked was, first, it borrowed a technique from the whaling industry from 1860, which was a method to shoot out a whale harpoon. I miniaturized this to shoot out a string, which I coated with silicone grease to make it sticky, and it popularly became called the sticky string experiment. The way it worked was a little gun shot this string out. It went about 50 yards across the surface of a field, then fell to the ground. Inside the instrument was a tiny electric motor powered by a battery. The motor then turned on and reeled the string back in on a little spool. When it was dragged across the surface of the ground, it picked up tiny grains of soil. That's all I needed, because those grains are covered with microorganisms. I needed only a tiny few specks, maybe as much as 100 milligrams of soil. When the spool was wound up, the radioactive nutrient was dumped on it. And if anything was alive, radioactive gas would come out of the spool, evolved by the microorganisms, would rise to the top of the machine, and there it would be detected by a radiation detector. So we monitored the evolution of gas as time went on over several hours of the experiment. We tried this on a field near our laboratory, and were surprised we got positive responses immediately. But those of you who have taken even high school science know that the most important part of an experiment is the control. This is the part that proves the experiment really did what you thought. If I just got a positive response, how could I know that it came from microorganisms and not some chemical in the soil? So the control that I made was the following. If I got a positive response, I would run a duplicate experiment with a duplicate instrument, going out and bringing in a sticky string with soil on it, just as in the first test. But now, before I dropped the radioactive material on it, I would drop a germicide, a strong germicide on it, hopefully to kill any microorganisms if they were present. Then I added the radioactive nutrient. If I still got a strong response, as in the first test, this meant that it wasn't a microorganism that was causing the release of gas, but some chemical. If, on the other hand, the response were strongly diminished or eliminated, that confirmed the fact that the first response came from microorganisms. When I ran that in our first field test, indeed, there was a nil response to the control sample. We had detected microorganisms. From there, we went on to a 10-year development program that not only developed 4 different versions of the instrument, but more importantly, selected the nutrients with which to test for microorganisms. How do you select nutrients to look for microorganisms that might be on another planet? Well, what we did was assume that Mars was created out of the same material as Earth, and therefore its initial condition would be pretty much similar to that of Earth, and it was from those ingredients and under those conditions that life might have evolved on Mars as it did on Earth. Therefore, we went to use the simplest, earliest organic materials thought to have developed on Earth. These were identified by the so-called Müller-Urey experiments in the early 50s. And these experiments used the materials on Earth in the atmosphere thought to have been present in the early atmosphere. Carbon dioxide, methane, water vapor, carbon monoxide, and exposed those to strokes of lightning. In the experiment, the gas was in a large tube, the lightning was sparks of electricity. After a couple of days, organic matter formed, dark blotches on the glass. These were analyzed, and it was those organic compounds that formed from which we selected materials to be used in our experiment. We selected 5 of them, tested them extensively to be sure that microorganisms responded to them. We never found any microorganisms not to respond to them, and therefore, on the basis of theory that they should have been or might have been the first organics formed on Mars as they might have been on Earth, and that microorganisms empirically responded to them, we thought they were pretty good bets. We tested hundreds of different kinds of microorganisms, pure species, mixed species, soils, field tests we made at the top of a mountain above the timberline, as you can see in the accompanying picture. Field tests we made on Death Valley, hot desert sands at the height of the day, and field tests on the very salty soil around the Salton Sea. In every case, we quickly detected living microorganisms. The experiment was never fooled. When we took soil samples and heated them to the control temperature that was specified by NASA, they wanted a different control than the germicide. They specified 160 degrees Celsius for 3 hours treatment of the duplicate soil sample. Then let it cool and test it. When we did that, in all of our field tests, we found a negative or nil response, confirming that the positive test responses were from microorganisms. After the 10 years of that development program, after many hundreds of tests established that the experiment was very effective and the control always worked and that the experiment could not be fooled by chemicals, we submitted a proposal to NASA when it announced openings for the Viking mission to Mars. In 1969, we learned that we had been selected as one of the life detection experiments to be developed for the actual mission. This was another 10-year effort. I was very fortunate in being able to induce Dr. Patricia Straat to join my company to help me work on this development. She was able to take my ideas and to work with the engineering company, TRW, that was putting them into hardware, and develop the instrument that eventually was flown to Mars. To do this, she even had to live for a while out with TRW in California to work very closely with the hardware development. It was remarkably successful. And we had a piece of that hardware in our laboratory back in Washington, D.C., where we could test microorganisms and be certain that we were getting the kind of instrument development that we needed. All went very well, although it was quite stressful, meeting the time demands of NASA to get ready for this experiment. Finally, the great day came, and blast-offs occurred in 1976 for the 10-month, 440 million mile journeys to Mars. Miraculously, the two spacecraft landed perfectly, some 4,000 miles apart as planned, and all of the experiments worked. We were very much surprised when we got our first result because it was positive. We got a strong positive curve seen on the picture, as you can see, and it was an immediate response very similar to the type we got on Earth with soils containing living microorganisms. We're very excited, but had to wait 8 days until the experiment was completed before we can start the control experiment. Well, you can imagine the intense feeling when we loaded the instrument with a control sample, heated it to 160 degrees centigrade for 3 hours, let it cool, and zapped it with the radioactive nutrient. Well, nothing happened. There was a nil response. Right there, we could have gone home. This was the proof that everyone agreed to before the mission that was needed to say, yes, there are living microorganisms on Mars. But not so fast. Nothing ever goes as planned, and scientists are eternally skeptical, as they should be, and especially about such an important experiment, which NASA had stated might be the most important experiment in the history of science if it detected living organisms on Mars. Doubts immediately began to arise, and we had to cope with these. Amongst the doubts, the strongest came when another experiment on Viking, called the molecular analysis experiment, which was designed to identify the organic compounds everyone knew must be on Mars. Just as on Earth, organic compounds were bombarding the planets, both of them, with comets, meteorites, and so-called interplanetary dust particles, which contain organic matter. That's how the Earth got its organic matter, from being bombarded from space. The same was undoubtedly true for its neighbor Mars. So our interest was in identifying those compounds on Mars, but the instrument called the GCMS not only did not identify any organic compounds, but it found none. Zero. It reported no organic matter. What a dilemma. NASA contemplated this, as did other scientists. How can you have life if you have no organic matter? It was decided there must be no life on Mars. There is some weird chemistry or physical effect that is mimicking life. No one doubted the results of the GCMS. Instead, they doubted the results of the label release experiment. Well, the first theory offered to explain away biology was that the label release response came from soil that had been activated by ultraviolet light. Because the ultraviolet light hitting Mars is many times as strong as that hitting Earth, since Mars has such a thin atmosphere. The theory was then ultraviolet light would prevent any life from forming and also would destroy all organic matter, and that would explain the results of both instruments. We were able, by some quick thinking, to destroy that theory. What we did was one morning on Mars, we sent the sampling arm out to a rock which had been sitting around undoubtedly for hundreds of thousands, maybe tens of millions of years. And at dawn, we moved the rock and quickly took a sample of the soil under it and put it in our labeled release experiment. And lo and behold, we got the same result as we got with the samples we took from the surface of the planet in the broad daylight. And the control also was nil. So we clearly showed the effect could not be from ultraviolet light. But then other theories promptly sprang up. In all, in a short time, some 40 theories sprang forward to explain that our results were caused by chemicals or physical activations of some kind. We diligently spent 3 years trying to reproduce the results we got on Mars, trying to reproduce them in our laboratory without using microorganisms, but many different chemicals. Those are the ones proposed. We were unsuccessful, and we were able to show that none of the 40 proposals really pertain to our experiment. Nonetheless, despite publishing these results, the theories remained that A, there was no organic matter on Mars, and B, there was a strong oxidant covering the surface of Mars that killed life and destroyed organic matter. C, that there was no liquid water on the surface of Mars. And then another complaint was lodged that in one of the experiments that we did on Mars that was not part of the original program, not required, but that we added on as a scientific curiosity, was to see whether after the experiment had run its 8-day course and the curve of evolving gas had flattened, if we injected a second dose of nutrient, what would happen? On Earth, commonly, you would get a second response as the organisms got new food and started digesting it, producing more gas. When we did this on Mars, however, we saw about 25% of the gas that had already been produced disappear. It had obviously been reabsorbed into the soil. So the people who felt we could not have detected life immediately said, that's not the way things are with biology, therefore it must be a chemical, and the soil must be basic or alkaline. When it's wet, it reabsorbs carbon dioxide that had been emitted. Well, let's go down those objections. We already showed that the ultraviolet light could not have produced the experiment. I guess then it was the organic matter that remained the strongest objection. We showed in a number of studies that the GCMS was not nearly as sensitive as our label release experiment. In fact, the experimenter of the GCMS said it took 3 million microorganisms in his test to render a positive for organic matter. Remember, I told you our experiment could detect 10 microorganisms. So we were 1 million times as sensitive as the organic analysis instrument. And therefore, it was quite possible. Both instruments were right. We detected microorganisms, but they were in small numbers that could not be detected by the organic analysis machine. Further research showed that there were other problems with the organic analysis machine. And just recently, as I will explain in a minute, it was impugned so that it no longer represents any threat to the results that the Viking label release experiment got. Let's go to no liquid water on Mars. Actually, Viking itself indicated liquid water on Mars when, during the rising day, the footpad temperature rose and got to the freezing point of 0 degrees centigrade and stopped rising for a while. This is indicative that ice is present, that when the melting point of ice is reached, the temperature does not keep rising because the energy of the increased temperature is used in melting the ice into water. And this is a signature for liquid water. That occurred. And even though we published that, it was not widely recognized. So my son, who by this time was a Ph.D. physicist, and I produced a paper showing that on the basis of thermodynamic theory, there must be liquid water in the soil of Mars, particularly and especially under the ice, which is shown in the photograph taken at the Viking 2 landing site. The so-called triple point of water was never exceeded on Mars at either Viking landing site during the entire missions. So therefore, the atmospheric pressure was always high enough to ensure that when the temperature rose above 0 degrees centigrade, which it did, that liquid water would form. Maybe just for a while, but microorganisms don't need long. But even beyond that, people wrote additional papers showing that liquid water forms in films in the tiny spaces between crystals of soil and even in the tiny spaces between crystals of ice. Enough for microorganisms. Indeed, in an experiment on the south pole of Earth, it was found that in ice that had never seen temperatures above minus 15 degrees centigrade, always been frozen, they found microorganisms living and metabolizing and reproducing. They were living between crystals of ice in the tiny films of water. Certainly, that could happen on Mars. I want to go back to the oxidant, the theoretical strong oxidant coating the surface of Mars. It was originally presumed to be hydrogen peroxide, but it turns out that several experiments looking for hydrogen peroxide in the atmosphere of Mars showed that there was essentially none there, far too little to have caused the results that we got. Now recently, something very extraordinary happened. The spacecraft Phoenix detected perchlorates in the soil of Mars. And scientists began to look at this and they said, hey, wait a minute, if there were perchlorates in Mars, the GCMS could not have worked to detect organic matter because the GCMS takes a soil sample and heats it to drive off vapors of organic matter that it then identifies. But if there were perchlorate in the soil at the Viking site, as there was at the Phoenix site, when the soil was heated, the perchlorates would explode and consume any organic matter in the soil. At about 300 degrees, perchlorates do suddenly decompose thermally and would destroy organic matter. Now, remember, in the label release experiment, the control was heated only to 160 degrees centigrade, and it was destroyed. So again, that couldn't have been perchlorates. But the presence of perchlorates could have vitiated the GCMS experiment. So it is now totally removed from the arguments against the label release having detected living microorganisms. Well, let's go back to summarize what the label release experiment found. In all, we ran 9 experiments, 4 experiment tests and 4 experiment controls. What we found was we got a response from soils that were heated to 10 degrees centigrade. That was the temperature we wanted to maintain to be sure that our nutrient would remain liquid. And that was a temperature experienced on the surface of Mars daily. So it didn't expose the organisms to any new feature in the environment. We found that if we heated the soil to less than 160 degrees, to 51 degrees, that we got a tiny response, 90% reduced from the initial response. In another experiment, when we heated the soil to only 46 degrees, the response was reduced by 70%. So here we had the kind of response to heat that you see with terrestrial microorganisms. If you want to distinguish between, let's say, the whole group of coliform organisms and the E. coli, the dangerous guys, you do this by incubating them 5 degrees apart. That separates them. The E. coli can withstand temperatures 5 degrees higher than the general band of coliform organisms. Very similar to what we saw on Mars. But then came what I think is a clincher. We wanted to do another experiment, but the engineers were afraid that we were now in winter and we might break the sampling arm by going out. So instead of going out, what we did was wait, in one instance, 3 months, and in the other instance, 5 months, holding the original active samples in the sample holders. We then tested them. And in each case, having held the sample in a dark box at 10 degrees centigrade, there were no responses after 3 months and 5 months. What kind of chemical reacts that way? We can't think of any, and neither can anyone else. We've asked them, and we've never had a positive response. But one could imagine that microorganisms taken out of their native environment and isolated from the daily cycle of light and dark, and not having any sunlight available, might readily have died. We looked in our library of responses, which we had accumulated prior to Viking, and there we found the answer also to the second injection. We found one Antarctic soil, and undoubtedly there are many, that when a second injection was made after an 8-day experiment, showed a reduction in the amount of gas that had already been evolved. It reacted the same, and you'll see a picture of that, as did the experiment with the second injection on Mars. So now we had answered all the questions. What could the remaining objections be? Well, I was trying to be conservative also. I didn't want to leap for that brass ring, which NASA said could be the most important experiment in the history of science. I didn't want to be wrong. So I studied the information of all the Viking experiments, all the new information that additional missions brought back from Mars, and also new information we were getting about life on Earth. We were all startled to learn that life is not a thin film delicately covering the surface of the Earth. Life is hardy. Even when the bomb goes off, we won't destroy the microorganisms that have gone into every niche on Earth. We have, since Viking, found life in the deepest parts that we have penetrated beneath the ocean, thousands of meters beneath the ocean, in the depths of the ocean, on clouds, on mountaintops, any place you can name that has been sampled has produced extraordinary forms of living organisms at very high temperatures, at very low temperatures, so that it's hard to imagine an environment other than perhaps in molten rock where there would be no microorganisms. This opens up the possibilities for Mars greatly. In addition, we've learned much more about the environment of Mars, and we have found no single thing that would prevent the existence and activity of organisms on Mars. Even microorganisms we know on Earth could live on Mars, such as the ones down on the South Polar Cap. Well, with this new knowledge, I decided as a scientist it was my obligation that now having become convinced that we had detected life on Mars to say so. And in 1997, I published a paper saying we had detected life on Mars. This was not received too valiantly. Many people strongly opposed it, even though they could not bring about strong arguments to the contrary. So, feeling quite frustrated again, I decided that the only way to drag these people who were so reluctant to change the paradigm that there could only be life on Earth was to construct another experiment. And I did that by doing what science is supposed to do, seizing on a positive result and expanding its beachhead to gain new knowledge. The positive result was obviously the label release experiment, because no one could deny that it got a positive response, whether it was from chemistry or from biology. When you get a positive response, you should investigate it further. The way I did that was to apply knowledge gained about life on Earth. Strangely enough, and for a reason no one knows, life on Earth metabolizes primarily only right-handed sugars and left-handed amino acids. And by that I mean, let's look at your hands. Your two hands, you would say, are identical. But are they? You cannot place one on top of the other. They're identical mirror images of each other. They're made of the same stuff, but they are different. Life metabolism works on enzymes. Enzymes use templates which very carefully select the compounds they work with by making them physically fit into the niches and grooves of the enzyme. So that an enzyme in a microorganism or in any life looking to pull in some good sugar for the organism to metabolize only fits right-handed sugar. And that's the only type it will take in. So it occurred to me that maybe what we can do now is something a little different than in the first Viking experiment, which experiments incorporated both left-handed and right-handed sugars and amino acids to be sure not to miss a different kind of life on Mars. We at that time had hoped we could send two instruments, one with left-handed and one with right-handed compounds, but NASA said no way we could use all that instrumentation. So what we did was combine the left-handed and right-handed compounds so we wouldn't miss an alien kind of life. But now I was saying, let's separate them. Let's send tiny dart-type experiments to land on the surface of Mars, ejected from a spacecraft that landed, to look for reactions with left-handed amino acids and right-handed amino acids separately, left-handed carbohydrates or sugars, right-handed sugars separately. And if we got separate reactions from, say, a left-handed amino acid that got a positive response, but a right-handed amino acid that did not, everybody I've talked to said they would pretty much agree that that was proof that the first reaction had come from living microorganisms. The most exciting thing, of course, would be if, unlike Earth, the life on Mars metabolized only right-handed amino acids and left-handed sugars. This would show it was a different form of life, something very exciting, and would indicate there must be life throughout the universe because it evolved separately on two different planets so close together as Earth and Mars. Well, since proposing that experiment, it did occur to me there was a loophole in it. Suppose the two results from the left-handed and right-handed experiments were the same. There might be an alien life that used both forms of the compound. So what I've done, as you can see in this picture, has been to construct the experiment instrument a little differently, so that now, in addition to looking for different responses from left-handed and right-handed molecules, in the event that it got a response or did not get a response either way, we would test with a heat control, like the original control on the Viking LR experiment. So that now, if we got a response, and we showed that by heating the control portion we got no response, no one would deny that was proof of life. I have proposed that experiment. It has not yet been funded. With the current economic situation, it doesn't look like there's much of a chance to get a new experiment to Mars for many years to come. Well, NASA spent $1 billion on the Viking mission to Mars. And it's my belief that if we really know that it detected life, we should not wait for another 10 years or more to verify that result. If the results we have do indeed prove the existence of life, that would change NASA's plans for future missions, for looking for life, certainly, and for sending men to Mars. Are you going to send men to Mars if it's contaminated with really unknown microorganisms? And of course, are you going to bring samples back from Mars, as is currently planned, take the chance that something in those samples might be very bad for our vegetation or animals or humans? So knowing the truth is very, very important. I have now proposed that what we do is convene a panel of independent scientists knowledgeable in astrobiology, and let me and some people who now agree with me, there are some 20 of us, present our point of view and the data. And then let those people who are knowledgeable and who can argue against life on Mars present their data, and have the panel deliberate and finally see whether there is enough strength in data to conclude either there is life on Mars or there is not life on Mars, and announce that result. And I think that is a very important thing that we should do. Furthermore, I believe it's the obligation of scientists, as I've stated, that once they have reached a conclusion, they must announce it, even if it's something that makes them uncomfortable. Secondly, other scientists are obligated not to say, well, the consensus is against it, but to state the specifics against it, or to examine it and decide that, yes, this is true. That's what I believe will happen if we do that, and I think it will have a major impact on the future of science. Thank you. Okay, Barry, it's good to have you here.
Thanks, Gil.
And I just want to tell you about your great book. Every year or two, I take it off the shelf and I read it again. And do you know, it's held up beautifully through the years. The amount of research you did to make a background for the search for life on Mars is excellent. And indeed, everything about it, from the snow algae on, lays a wonderful setting for the experiment to look for life on Mars. Everything in the book backs up my ultimate claim that, yeah, we did find life on Mars. And I admit, it took me, 20 years before I finally said, hey, the facts are so compelling that I got to say it. And even though I knew it was going to make the world mad as hell at me, especially when Chuck Klein and Jerry Softman kept telling me not to say anything, I felt I had to say it, because otherwise I couldn't classify myself as a scientist. I believe when the scientist reaches a conclusion, he's obligated by ethics to state it, whether people like it or not. And similarly, I think now scientific ethics require that astrobiologists look afresh at these data and reach a conclusion. It's not enough to say, well, it might be so, let's wait for the next mission. The next mission isn't going to come for 10 or 20 years, and the next mission is being planned based on there is no life on Mars, as are manned missions to Mars. So if indeed we know now there is life on Mars, it'll change the whole program of NASA, and also it will change many other things about life on Earth. So I think it's an obligation on the part of the scientific community to look at these data afresh and see whether a conclusion can be drawn. If so, we're way ahead of the game. If not, let's say, hey, there is no proof. Let's continue finding out whether there's life on Mars or elsewhere. Anyway, as I review the book, it takes me back, of course, and here I just flip it open to a page of Wolf Vishniak and Pat Straat. He's in his Arctic outfit just before he went down to the Antarctic, lost his life. But, you know, this was a long path going to Mars. Began in 1958 when I first wrote a proposal for NASA, and ended when our final contract ended in 1980. We did have 3 years of work after the mission ended. We proposed to NASA to do laboratory work, to try and discriminate between a biological response to our system or a chemical response or physical one. And NASA said they would only fund the study if we limited it to looking for chemical and physical explanations, no biological ones. Well, there again, that's not quite scientific, is it? You're supposed to explore both sides of an issue, but they didn't want that. But we took the contract and worked for 3 years very diligently, trying to find a way to explain the results we got without using microorganisms. And we were not able to do it. And since then, in all these years, 34 years since we got our results, no one has been able to produce in the laboratory or even in theory any material or physical activity that would duplicate not just the initial positive response, because that's kind of easy to duplicate, but the controls, the thermal controls. They just defy chemical answers. So those are the things I would like to see considered. They have not been adequately considered. Most of the time when scientists say, the LR did not find life on Mars, and you say, why do you say that? They say, oh, it's the consensus of the scientists. Well, consensus is not the way that science goes. By its very definition, science is not a democratic process. It's never a majority that discovers something new. It's always one person. And the majority is almost always against that finding, because, especially if it's a major finding, because they've been taught what the truth is when they went through school. And it did not include, of course, the new finding, which startles the understanding that they had prior to the new finding. So it takes a long time before, as they say, the paradigm is broken. And this book was the first step towards breaking that paradigm about there being no life outside of the Earth. So I believe that as time goes on, your book's going to be recognized as a signal effort in founding, really, the now science of astrobiology. And I'm very thankful to you for having seen very early in the game that there was some merit in the label release experiment, and to have devoted so much of your book to covering that experiment and then giving me an opportunity at the end to contribute a chapter explaining my position. And of course, the book was released simultaneously with the paper I gave and had printed in the SPI annual meeting and proceedings of 1997. So the paper and the book debuted simultaneously and made an impact on the astrobiological world, although at that time it certainly could not be construed as a favorable impact, and we took a lot of abuse for it, and we still take abuse. But I have been keeping tabs, and in recent years, believe it or not, I've got 20 plus, I think it's about 22 scientists, prominent scientists, who now say, yes, they believe that I did find life on Mars. And interestingly enough, just last week, in a meeting in which I participated with Chris McKay, he said, Gil, you know, I think the biological explanation is becoming more probable. So what more can you ask? Well, what more I do ask is that we get the Chris McKays of this world together and consider the evidence, which has not been done since 1977. That's the last time the National Science Foundation convened a meeting to review the evidence and concluded that we did not detect life on Mars. We've learned an awful lot since then. Isn't it time to get a group together again, not those old prejudiced old-timers, but the new crop of astrobiologists who have open minds and who will listen and evaluate and decide. Am I correct in concluding that the label release experiment detected life on Mars, or am I overreaching? Thanks, Larry.
Thank you.
One of the things that was said very soon after we got our positive response on Mars was it was too much too soon. Well, that's not the case. This graph shows responses that we got on Earth using the LR technique and the response we got on Mars. The track in red is the Martian response, and you can see it's well down at the lower end of the range we got on Earth, and it's right near the ones that we obtained from samples from the Antarctic. Sounds, right on target to me. Amongst the many important things that were found on Mars and Earth that bear on life on Mars, perhaps the most astounding was the finding that Mars and Earth have been swapping pieces of rock and soil for billions of years. It turns out, as seen in the accompanying picture, that meteorites hit Earth, for example, and eject great clods of soil and rock into space, some of which, a tiny fraction, but some of which eventually lands on Mars. What has been done, the astounding part, is in laboratories on Earth, experiments have been made to show that living microorganisms would survive the impact of the meteor on Earth, the ejection of the material through the Earth's atmosphere, and through a long voyage through space, which could even take hundreds of thousands of years before finally some of it lands on Mars. They would survive the entry and the landing on Mars in growing form, absolutely viable. Each segment of this trip has been tested in the laboratory. Of course, not for hundreds of thousands of years, but it is known if you want to save microorganisms indefinitely, you freeze dry them. And that's exactly what happens in space. So here we now have a situation where there's no longer any doubt that Mars must have been contaminated with living microorganisms from Earth, and of course, vice versa. So they've been swapping microorganisms for some time. All of that finally bears on Carl Sagan's famous statement, extraordinary claims require extraordinary evidence. And at his time, he thought that it was extraordinary to claim that there is life on Mars. Now, with all that's known about life on Earth the conditions on Mars and the swapping of materials between Earth and Mars, the claim is no longer extraordinary. Indeed, it would be extraordinary if Mars were sterile. And the evidence that's been accumulating since Sagan's statement has gone from ordinary to extraordinary. So I submit that his statement has been fully met now, and that the claim is now ordinary, and the evidence is now extraordinary for life on Mars today. This shows a cartoon of Earth and Mars, and it shows how a meteorite impacting the Earth would explode and drive materials from Earth up into outer space, where they would go in every direction, some of which, a tiny amount, but some of which would eventually find their way into the gravity well of Mars and be pulled into Mars and land on the Mars surface. So this shows every element of the impact on Earth, the ejection of the material through the Earth's atmosphere, the travel through the cold vacuum of space, the entry through the atmosphere and heating thereby of Mars, and the impact on the surface of Mars. And each segment of this trip has been duplicated in the laboratory to the point where researchers claim that living microorganisms have undoubtedly been ejected from Earth and landed on Mars in viable condition, and we now know the conditions on Mars would support many types of microorganisms growing on Earth.